Hi, this is Roger from Kanka Labs, and today it's about the popular ULN2803, a Darlington driver chip, or as you see, it's a whole family ranging from 2801A up to 2805A. We'll talk about the differences later. As I've handwritten here, they are so-called low-side or sync drivers. So what many don't know, there is a companion series of ICs which are so-called HighSide drivers. The UDN, not ULN, UDN2981 through 2984. We'll talk about them in the end. You can do nice things with them. For example, they go up to 80 volts. They can switch up to 80 volts. Anyway, let's go back to the basic data of the ULN280x series. The output current can be up to 500 milliamps, but be aware this is not true if all outputs are switched on at the same time. We'll also talk about this later, about what the datasheet tells us in detail. The IC can switch considerably high voltage. 50 volts is quite high. We have integral suppression diodes. That's what you see here. Each output has a so-called freewheeling diode, and they all are tied together to a common output or a common pin. And we have versions, and that's the difference between the different numbers for all popular logic families, so not only TTL and 5-volt CMOS, but also other logic families. And what many don't know, the outputs can be paralleled. But let's start with the use of these, or what's the intention behind these 8 freewheeling diodes. So when you apply a load to the output, and the output is the collector of an NPN Darlington, all the emitters of the 8 Darlington transistors are tied also to a common pin, to a common ground. Now let's suppose you're switching an inductive load, which can be a relay coil or a magnet or something like that, and you connect them to VCC. So that's this is here the pinout of, let's say, output 1, 2, 3, 4, 5, or up to 8. And your load is always connected to a positive voltage on the other side. So that's why they call low-side drivers. When this transistor turns on, it pulls the load to ground, to the low side of your power. Now, what happens when you switch on an inductive load like the relay coil? Well, when you switch it on, there is nothing that can do any harm happening. The current will rise linearly, so there's no problem. But what happens when you switch it off? Well, then due to the breakdown of the magnetic field, you will get an induction with reversed polarity. So if we beforehand had the positive side here and the negative side of the load here, now induction will create a positive voltage here and a negative voltage here. And this voltage can be hundreds, sometimes even thousands of volts, and that would destroy the output transistor if we don't have any means to get rid of this voltage. Now, simple as it is, just use a diode, and now the induction generated voltage and current will circulate here, and the voltage here is safely on the collector of the output transistor is safely limited. And this is what it's called a freewheeling diode, because when you switch the power supply of an inductive load, when you switch it off, then the inductor is hanging in the air, it's freewheeling, and to get away with the high generated induction voltage, just use the freewheeling diode. And as you can see, it's exactly as they have already integrated this one here. They all have a common connection, and this common connection you have to, and this would be here, you have to connect this, this is pin number 10 of the IC, you have to connect this to the positive voltage of your supply for your loads. So that's a nice feature that you don't need any external diodes for switching inductive loads. And now I hope this became clear how you use it. And now let's go over to the other specific details of the ULN280x series. So here we see the schematic of the 5 different types. As you can see, they all have the freewheeling diode, they all have a discretely built NPN Darlington transistor with integrated base emitter resistors, and the difference is the range of the base emitter resistance and depending on the family type, a base resistor. So let's take a look at the 5 different types. The first one, the 2801A, is for PMOS, which is in today's world not used anymore, but also for CMOS. The ULN2803 is for 14 to 15 volt PMOS, also not used very often today. And the most used one is the universal type for 5 volt TTL, and that is important for 5 volt CMOS. You will also be able to switch the Darlingtons on with 3.3 volts, although they are basically specified for 5 volts. So if you have a microcontroller output with 3.3 volts high, they also will safely turn on the output if you're using the universal type 2803A. But also today, still CMOS is still used, the standard CMOS, not the HC CMOS, is also still used because standard CMOS is capable going up to a voltage of 15, or some ICs even can go up to 18 volts. That can be quite nice in some analog or digital circuitry to have 15 volt switching capacity. And if you're using CMOS with higher than 6 volt VCC, then you should or have to use the ULN2804A. The 04 is important because it has a different base resistor. Otherwise, the current from a high output from a 15 volt CMOS there would be too much base current, and that drops, or that draws the CMOS down, and the current is then, the base current would be higher than is usually allowed with standard CMOS. And we have a last one, the 2805, that is for high out TTL. I'm not sure what they mean by high out TTL, so perhaps somebody can give an explanation in the comments. But the 2 types that are mostly used is the universal 5 volt one, which you can connect to basically all 3.3 to 5 volt digital outputs, no matter if they are TTL or CMOS. And the second most used one is the 2804 for, let's call it, high voltage CMOS or PMOS, if you still have any ICs that are working with PMOS. So let's take a closer look at the data sheet. We had the output voltage of 50 volt, the 500 milliamps max continuous collector current that we already knew. But what you also should take into consideration, the collector emitter saturation voltage can be as high as 1.3 volts, even in the worst case 1.6 volts. So if you're working with only a power supply of, let's say, 5 volts, and you're switching really 500 milliamps at one output, then here on the collector emitter we can have up to 1.6, or what was the highest? Yeah, in worst case you have to take into consideration there could be already, out of this 5 volt that you are using here, 1.6 volts can be at the collector emitter, so there are remaining only 3.4 volts, and your load should be safely working also when taking into consideration this missing 1.6 volts. So next is the turn on and turn off delay time, which might look with a quarter of a microsecond or 250 nanosecond, that might look relatively fast, but in today's world of fast microcontrollers, you can get a problem if you're switching, for example, in multiplexing big LED matrices. This can be a problem even with an Arduino with its 16 megahertz frequency. You have to take this quarter of a microsecond into consideration, so that you don't get into the situation that perhaps two outputs are conducting because you didn't realize that it takes some time for one output to switch off and also for the next one to switch on. And now finally we take a look at the true output current that you can get. We already know 500 milliamps is the max output current you can get, but the recommended maximum current is only 400 milliamps. And now it depends on how many outputs you are using at the same time. So if you think that you can turn all 8 outputs on in parallel and get 500 milliamps out of them, no, you don't get. With a what's called the duty cycle of 100%, that means all are turned on the whole time, you only get 150 milliamps per output. So if you multiply this, then you get a total output current summed up of 1.2 amps, but only from all outputs if they are paralleled, or each one will give you only 150 milliamps. Now for the 400 milliamps limit for continuously turned on outputs is only valid for a max of 2 outputs. Here we still just can get 2 outputs with a duty cycle of 100%, which means always on. 2 outputs can really supply 400 milliamps at the same time for an extended period. But if you are multiplexing and you know, mustn't be multiplexing, but anyway, if the outputs are not turned on the whole time, then let's take the maximum. If you are really using all 8 outputs turned on, but only for, let's say, 28% of the time, which means you have a PWM signal where the on time is 28% of the period, or in other words, the off time would be 72%, then you can really get 400 milliamps out of all 8 outputs if it's not for an extended period, but only for roughly a quarter of a period. So that you should know for not destroying your circuit, or in other words, to build a reliable power circuit. So, and as promised, we finally take a look at the companion series to the ULN280x, the UDN2981 through 2984. The different numbering is again for the different logic families, and there is still there are two differences. The first one we already saw, they are so-called high-side drivers, which looks like this. You have your driver, and the driver is connected with the positive voltage now, and the output of the driver, now the load goes to ground, and that's why it's called high-side drivers, because VCC is now switched to the load, and the loads, if you have some of them, have a common ground connection. This is sometimes necessary, for example, when switching VFD displays, vacuum fluorescent displays, which I'll make a separate tutorial about. It's quite handy to have high-side drivers, and their internal structure is a bit more complicated, because it's easier for IC manufacturers to build power NPN transistors. You will see we have 1, 2, 3, 4 NPN transistors and only one PNP. So they must make some effort in silicon to get this high-side driver switching. Here you can see they have a common connection to the positive power supply, and the output then is here. The positive power supply is switched from the high side to the load. Compare this again to the low-side drivers. There are only 2 transistors plus the freewheeling diode. As you can see, we apparently do not have a freewheeling diode, because usually you don't. Sorry, I was wrong. Of course we have them here, but of course in reverse direction. Here we have the freewheeling diode going away from the collector of the output, and here we have the direction to the output, from the common ground to the output of the driver. There's one nice thing about them. There is a standard type which can be used with a supply voltage from 5 to 50 volt. That's exactly what the ULN280x Low-Side drivers can do. But there is also a part of the family that can go, I'll make it a little bit bigger so that you can better see it. There is also a family type that can drive up to 80 volts. That's quite high already, but not lower than 35 volts. So you even have the option here to drive for us low power guys and low voltage guys comparatively or relatively high voltages. And perhaps in my video about vacuum fluorescent display, I'll show you an application of this IC, which I was quite lucky that I found this IC by chance, and it saved me a lot of silicon or discrete transistors when switching a VFD display. So that was it for today. Some infos about the ULN280x Low-Side and the 298x High-Side drivers. Thanks for watching. Until next time, bye from Kainka Labs, bye from Roger.